Thank you for the introduction, and thanks to all of the organizers for inviting me, and also for letting me stay here for the whole winter term during all the workshops. It was quite interesting. So the work I'm going to talk about today is more on the phylogeny side of things. So, and it's the work that I was doing with my PhD student, Popovic-Rivas. So the motivation for this is, doing phylogenies with different phenotypes. So you sort of imagine a finite number of phenotypes that you're interested in studying and trying to figure out a phylogenetic tree on these different types. So, you can think of things like wingless and not and winged insects, or self-incompatible and self-compatible plants. So there is some switching between the phenotypes, in the sense that you can have a winged species that becomes wingless and then becomes winged again. So essentially the biologists or theoretical biologists who have been investigating this run branching processes with multiple types, and then sort of figure out the phylogeny by running simulations and trying to figure out, if I'm at a certain step at a certain time, what is the chance that will eventually give me this this different distribution of species at the tips. And this is all very well, and I think some of the simulation software that is around, like BISSY that Fitzjohn and Otto have, and Classy that Goldberg and Igich developed, they run very nicely, but I was curious what one can say mathematically about phylogenetic trees on different types, and whether, maybe that can be helpful for some of the quantitative biology analysis. So what I'm going to start with is a branching process on with multiple types. So you should imagine, so for the first part, well, for most of the talk, I'm going to do discrete time branching processes. And so we have a setting of a Galton-Watson tree, and then you have a certain offspring distribution, and each parent has a different random variable. Each type of parent has a different offspring distribution with which it can give offspring of different types. So, in this sort of graphical representation, you have two types, and you see that, each of the types can give different number of offspring for its children, for their types. Okay, so let me just go back for a second. So here we have the full tree, full genealogy of these things. But of course, phylogenetic trees basically want to go, and just chop off all of the leaves and say something about the trees, the reduced tree or the ancestral tree that you get if you eliminate all of the offspring that did not make it to some present time. So one of the ways that we decided to look at this is based on a coalescent point process representation of phylogenetic trees that I'm going to first describe in a single type setting, which was an idea that Amory sort of introduced to me, and then we sort of wrote some results about the distribution of the phylogeny based on this point process representation. So to explain this, essentially, you embed the full tree in a plane, and in such a way that things don't overlap, so you're sort of putting it on a grid. And essentially, you look for the first individual at the present time in the present population, and there's some sort of spine that goes down, genealogical spine that goes down from it, and then you look at all the other present individuals as to how they're related to the individual before it. So in some sense, it's not a coalescent picture that goes, I have a certain number of types here, and then I'm coalescing down. So I have events in time that I'm running a Markov process backwards in time that way, sort of horizontally, but you're writing, am I saying that right? Vertically. Here you're running things horizontally. You're going to have a certain kind of construction that sort of runs horizontally, which means you're including more and more of the present individuals in building your tree. So what you have here is you're trying to stick on the genealogy of the individuals one by one, so the individual 2, then the individual 3, then once you get to the... This is what my computer does. So you're slowly attaching edges. It'll come back. So I need to touch it often enough, I guess. So you're building on the genealogy of the individuals that are present at a certain time, and you see that when you do that, you will avoid all the leaves that you have in the process. So the quantities that you are interested in if you're building a phylogeny is essentially the depths at which you attach the different types. So if you think about this quantity AI, that's the coalescent time. So between when I have individual 2, its coalescent time with the previous individual is only 1 depth. If I have individual 6, then its coalescent time with the individual 1 is way down here, and then 7 is going to have a coalescent time next to 6. So in this way, so this depth, then 3 has the same depth, then 4 has this depth with 3, 5 has a short depth with 4, 6 has a very deep depth with 5. You're slowly building exactly the kind of points that will give you a phylogenetic tree that you can then reconstruct the same way that you would if you just got points from which one came first in a coalescent point process going vertically downwards. So the kind of ingredients that you have to keep track of is essentially at each point you need to, in this picture, you need to keep track of if this individual, which one do I want to pick? This individual here has 3 offspring. How many of those will have any descendants surviving to the present time? And in addition, okay, so for instance, this one has 3, but by the time you come to the individual 3, only one of them is left. Okay, so because of multiple offspring in the branching process, you tell myself what will happen, and then I don't follow my advice. So because of multiple offspring numbers, you not only have to know how many of them will have descendants in the future, but you also have to know how many you've already seen. So in a sense, because you're going horizontally, you have to keep track of, you sort of have to keep reducing the number of offspring that will have descendants as you move along horizontally.
By going horizontal, you mean you're sort of adding one at a time and then keeping track of that?
So,
with the others?
so essentially, you sort of put random variables. I keep touching that and thinking that will keep this good. So if you go in this picture, you can essentially tack them all along this spine first. I mean, it depends how you want to construct this. You can tack these on and then figure out, if you're doing a construction, you can figure out how many of these this guy's going to have, and then you proceed to the next one, and then you put them on, and then, for instance, this guy had only 2 that are going to make it up, right? So it only has one other descendant that's going to make it up, and then here you sort of get independent branching events because you have a spine that you now are free to choose how many offspring you have here. I'm confusing you. Okay, let's see if it gets better. Should have let Amory explain this part. So if you keep track of these quantities, then essentially you can build this process. You can show that this is a Markov chain horizontally. And this process, so not the process of just the depths, but the process where you're keeping track of how many descendants you still haven't seen, so how many offspring you still, that have descendants in the future you still haven't seen. So that has a Markovian property. And then from that, so that's this process DIN, and then the coalescent depths are a simple function of that, because you're just looking at, the first time where, the first, let's see, the first dip here that where there's nothing here. All right, so this sort of explains this in a sort of more sparse picture so that you can see it. So you build the individuals going down with the number of offspring that will have some descendants, and then as you're exploring this process, you keep eliminating the ones that you've already seen. And essentially that will allow you then to reconstruct the whole phylogeny. All right, so the result that we had in our paper was that essentially you can write this process down as a Markov chain, and the transitions are such that everything, so you start with a first, you start with the first individual, you are free to sort of independently put the offspring down with a certain distribution that is using the fact that all those individuals at the different times will have descendants in the future, so that's why you have this conditioning over here. And then as you proceed, the next individual, you look for its depth, right? And then for that individual, anything below its depth, you have to keep the same as the previous individual, because that's part of the spine still. And anything above your coalescence time, you can now tack on to this. So for instance, in this picture, once you see that this is your coalescent time for the individual 6, you have to keep all of this stuff intact. So all of this part of your sequence you have to keep in your process, but this part you're allowed to build from new random variables, because this portion, this sort of subtree, is independent of what has happened here.
So could you just walk us through one step of the Markov chain, was in the was going from I to I plus, I guess it's not one step to the Markov chain, but take us from
sure.
one
So,
step.
Okay, so let me just make sure this doesn't go down. Yeah, I can probably do it here. So the Markov chain is each time, or so time is not time, but it's so it's labeled by the individuals at the present time, right? That's what would usually be thought of as time in a Markov chain, right? So this is your first, so this is your first element, and it has a sequence. It's a sequence valued point, right? So, and the sequence consists of how many individuals this ancestor have. So how many offspring does it have that will make it to the present day? Then this depth as well. So this one has 2 in addition to the spine. This one has 1 in addition to the spine. These ones have 0, 0, 0, 0, and this one has 1, right? So the first element of the chain would be 2, 1, 0, 0, 0, 1, okay? And then the next one has the shifted first point, and then this stays the same. All of these depths stay the same, but here there's no room to add new stuff because you're in discrete time. But here, for instance, all of this stays the same. So D6 has all of this part the same as D1, but then here it has new ingredients. So it has 1 at this level, 0, 2 at this level, 0, 0, 0. Okay? So you think of it as a sequence of natural numbers at each point, at each step of the chain.
But do I need to think of it as a sequence, or is each end its own independent Markov chain?
No, it's not. You need to think of it as a sequence, right? The depth is not by itself giving you anything. You have to keep track of you think of it as a spine. Think of each one of these things being a spine, and then I'm kind of changing the shape of the spine in some Markovian way. So you think of it as a Markov chain on spines, but on the spine I'm only going to record values at these branch points. Does that make sense? So you have to, the spine is evolving in a Markovian way, not like you can't just look at levels. Okay. So what happens now if I want to do this in a multiple types setting? Well, because the offspring distribution depends on the parent type, I'm obviously going to have to record not just the number of offspring, but I'm going to have to record what type that ancestor is and what type the offspring were. So now I go back into this picture and I just sort of enlarge the state space of my, spine of my Markov chain. And the way I enlarge it is at every point, this DI, as opposed to being just a natural number at each depth n, this DI is now a sequence of types. Okay, so now at this point, before I had, I said, this guy has everything the same as here, but here it's allowed to just put, and I had some numbers, right? Here it had 1, and here it had zeros, here it had 2, and here 0, etc. Now here I have type, a sequence of types. So instead of coding just 1, I'm coding a vector of types. So as I go down, if it's 0, well, then that's an empty set here. But here, I have to encode these types. Okay, so I have a vector of types at each point of what are my types of my offspring that are going to have descendants in the future. Okay, and so because of the whole sort of, the Markovian property doesn't change in terms of the tree structure if you keep record of the types. So that whole aspect of why you still, again, get a Markov chain still holds if you just enlarge the state space this way. So that part of the sort of proof is relatively straightforward and probably perfect for a PhD student to do. Hopefully I wasn't, cruel by making her do all the notation. But essentially, again, you can show that you have a Markov chain in which you can construct things where, again, everything below, so AI is the depth at which you're attaching to your previous the spine of the existing individual. And so below that, you have to keep your chain. At that level, you shift the number of types, right? Like you erase the first one because you've seen that one. So you're just keeping, this is just a shift by 1 this way. So you drop the first guy, right? As I said, you record the vector of types. Now you just drop the first guy and you shift everybody by 1. And then above it, so this is kind of written funny where n is going downwards, but for all the depths above, now I get to pick again I get to pick independent variables. Except here, before, I was allowed to pick independent variables, right? In the single type setting, I was allowed to just pick, independent variables at each one of these points. Here, I can't really do that. What I have to do is pick a whole spine at once, because, how many things I have here depends on what type they are, and I don't know what type they are unless I know, what its parent was doing. So at this point, essentially, everything here stays the same. This guy gets eliminated, so I remain with this vector. Well, this guy is not there because he doesn't have descendants. So I have 2 things. So I've eliminated this guy. I stay with just 1 point. But here, then, I get to tack along all of the. I have to, encode all of the individuals, the types of these individuals along the spine. So if you, use that distribution as this eta here that I've encoded, then you again have this Markov chain in which you can build this phylogenetic tree. So maybe this will illustrate how it's going. So say you take first a spine, And then you build, the gray shaded guys are the ones who are not going to have individuals that make it. And then the dark shaded guys are the ones who are. So at this point, I've built up the 2 and 3 parts. And then, to start off with the guy who's going to make it, then I've built up the 4, 5. And so when I'm building 6, I have to choose, I know which offspring this guy is going to have because of my earlier construction along this whole spine. So I know the type of this guy. So now I can sample from this distribution. I can make some of them, from the usual offspring distribution of a parent of this type. I kill some of them because they're not going to make it to, I kill them independently based on the probability of making it to this time. And then the ones that make it, you start by, you build the spine of this guy, and then you'll eventually get to later on building the spine based on the other guys. So that's what this does. All right, so what kind of features can you extract from this tree? All right, so one of the things that you are interested in when you're when you have a phylogenetic tree is the distribution of edge lengths, for instance, in this tree, because it sort of tells you something about the shape of the tree. So you can, from this construction, you can extract the first you can extract obviously the depths of all the consecutive individuals, right? That's just comes from how the tree was built. Now, I might be interested, because I have multiple types, now there's sort of extra features in the tree that I might be interested in, such as how deep are the coalescence times of individuals that are of the same type. So, here, okay, these 3 are all of the same type, so they, I'm just using the real, coalescence time here. But then the next guy of the same type is all the way here. And so I may be interested in how long then till I link up to this guy. And then the next guy of that type is all the way here, so I would have to extract this length to figure out. So as you can see, not the same type coalescence points are not necessarily filling up the set of all coalescence points, because you have this interspersal of individuals. So this coalescent time is not going to appear anywhere in the same type stuff, because it doesn't appear as a coalescent time of this guy, and it doesn't appear as a coalescent time of that guy and that guy. So some of the points that are just sort of, so the coalescence points of same type individuals are a subset of the full coalescence time.
Sorry, wait.
Yeah.
So next means in terms of this embedding here. So
Yes.
what sort of kind of biological, this significance does that have, right? You haven't sort of like taken a
I don't have an answer.
haven't taken a
None.
random sample from something. Okay.
Yeah.
Okay.
So yeah, this all depends on the embedding of things in the plant. So the next may mean nothing in terms of biology, unless for some reason you've. So you can write down formula that describe, based on the offspring distribution, you can write down formula that tell you what is the distribution of, this is just of consecutive individuals, and this is of the distribution of coalescence times for a specific type L. Okay, and it's it's a messy formula that isn't particularly pleasant because, well, you're just using the generating function of the offspring distribution. However, now we come to a special case that's particularly nice to analyze. So in the single type setting, if you have a geometric offspring distribution, then you have a lot of nice features of the phylogenetic tree, because you have a lot of independence properties. So sort of the analogous thing for that in a multitype setting are multitype linear fractional offspring distribution. Okay, so in a single type setting, you would have, again, it is a linear fractional distribution, but here it's extended to multiple types. And it has this, the reason why it's particularly nice is that the offspring, essentially somehow the dependence of the parent type is seen kind of only in the first offspring or in one offspring, which you sort of place as first in this embedding. And then the rest are not parent type dependent. Okay, so there's a lot of memoryless that gets built into just this offspring distribution, but it's not completely useless, as you'll see in some. I mean, it still has it retains some multitype features in it. So this is sort of just what the generating function of a multitype distribution would be, and the results that were obtained before is that essentially, if you have that kind of offspring distribution, then the distribution of the offspring that are in the nth generation also has that same form. So where the parameters are given by some matrix iterations from the original type. So you know a lot about what the types of individuals at generation n will be if you have such a nice offspring distribution. So in that case, I guess it's not that surprising, but it's not immediately obvious that now your coalescence times end up somehow completely forgetting about the type of the parent. So you can show that in that picture, the coalescence times of consecutive things are completely independent of what the individual at that depth, what its type was. So you get very simple formulas based, with a single parameter that you computed using that matrix iteration. And the same thing holds obviously for coalescence times of same type individuals, except it just you just depend on which is the type of individual you're looking for. Same, its next existent species. I mean, type in the current distribution. So essentially, in the multitype linear fractional setting, you have a very nice structure because this is no longer a complicated Markov chain. It's just a sequence of independent, identically distributed random variables as you go along.
Is the linear fractional case, does it sort of behave in a special way, or is it just that you can analyze it?
It behaves in a special way. I mean,
so you're saying the statistical properties are somehow very special.
Yeah.
If you compose these generating functions with themselves, you stay in the same function.
No, I understand that, but that's a sort of solvable.
I mean, okay, let me put it this way. If you look at the single type setting, yes, the geometric offspring distribution is special, but in the rescaled limit, it gives you the same tree as a lot of the other distributions. I don't think that's the case here. I think the multitype one is a little more special than that. Yeah. However, so suppose now, so you think, okay, do I still see features of this offspring distribution in the shape of my tree or in the statistics of these coalescent times? And you can, the simplest thing that we looked at is, okay, let's look at the offspring distribution of two types, where in one case you have a very symmetric type of relationship between the two types. So the offspring distribution is such that you give individuals of the same type as yourself with probability p, and you give individuals of the other type with probability 1 minus p, but it's the same for both parents. Okay? And the other one is the asymmetric case, where you sort of feel like, okay, I can go from wing to wingless, but I cannot get my wing back afterwards. So you have no chance of giving, if you're type 2, you have no chance of giving an offspring of type 1. Okay? And it's very, if you look at what you get then in the tree, essentially you can show there's a sort of there's a stochastic dominance of the distribution of coalescent types in the asymmetric case versus the symmetric case because so the guys of type 2, which only gave their own type, are going to have shorter coalescence times for the same type coalescence times than the guys in the asymmetric case, because essentially they create only subtrees of their own type. Okay, whereas it's the other way around for the type 1. Okay, so you can sort of show that you have complete, stochastic, you have asymmetry in the distributions of the coalescence times as well. Okay, and of course, if you just look at the symmetric distribution and you look at what was that chance of switching to the other type, if it's bigger than 1/2, then again you can show that the depths of where the 1s connect is going to be greater than where the 2s connect, because you have a higher chance of switching. So here is also if you have more of type 1s. Okay, so you can sort of do all sorts of things like this. And that's nice, but here's, what this generates is, so you start with some branching process, the offspring, or you assume some offspring distribution, and so then, this kind of coalescent process allows you to simulate these trees or to describe the distribution or some features of this tree. But, I wanted to see, is there something, is there some way of sort of going back, right? So inferring from, let's say, knowing what the tree looks like, can you now, or at least something about the current state situation or a very recent situation, let's say a couple of generations back, can you infer something about which is the branching process, which is the branching mechanism that gave rise to this tree? Okay, so in the single type setting, you sort of, there aren't even good ways of describing shapes of trees, but if you assume things are neutral, then essentially any kind of branching process that you put down in this that's critical will, when you prune stuff, the shape modulo the branch lengths will look like a Yule tree. So by shape here, I mean forget about how long exactly the branches are, just keep the actual shape of the tree. So that's sort of your prototype phylogeny in a single type case, so which you would get if you just had a birth-death process. So now if I have a multitype, something like a multitype birth and death process, and I start, now I'm in continuous time, I have a 2-type birth and death process. If I start pruning away all the individuals in the genealogy that didn't make it to today, I will end up with something that's distributed as a multi-type Yule tree. So a Yule tree is the genealogy of a pure birth process. So the multi-type pure birth process would be one where, at some rate I give offspring, different rates for different types of parents and different types of offspring. But I also can switch to another type along my lineage in continuous time. And that's because essentially I may have given birth, so I was of a certain type, but I gave birth to another type. I didn't make it to the top, but the other type did. So that's sort of the event in the tree that you would see as switching color. So you have not just in the single type, you just had pure births, right? Here you have births of different rates for different types, but you also have a switch of color along the tree. So a switch of type along just one lineage. And so what are the features? So if you look at the present day stuff, what are the things that can maybe retain some of the information about these rates of switching and the rates of giving birth to different types? Things like the leaf configuration or the pendant configuration so the leaf configuration tells you how many different types you have at the tips, but the cluster configuration kind of should retain some information because that's sort of the last coalescent time event in the past, and that will tell you sort of the chance that you will have had children of a certain kind. So what we looked at is trying to figure out results on the number of cherries. So in a 2-type setting, we did it for K-types. So the pictures illustrate you have many cherries of different types. You have many pendants of different types. So pendant is just a leaf that has a single edge going back, whereas a cherry is one that coalesces with another leaf one generation back. So if you look at, you can write a simple set of equations for the mean number of, you need to retain the mean number of leaves overall, since you're in continuous time. You need to retain the mean number of cherries of the different types and the mean number of pendants of different types. You can write this set of equations, and then what I wanted to look at is, can you now infer back what the rates are if you know these amounts? Now, at a fixed time, that's a little tricky. If you assume time is very large, so you've taken, in these equations, you've taken a limit as t goes to infinity, so you're in some kind of stationarity, then you can revert the set of equations back, so that based on knowing what's the proportion of the different type of cherries and what's the proportion of the different type of pendants, you can recover the rates of the multi-type yield tree.
So the pendants and the cherries is just going one generation back?
Yeah. Yeah. So that's why it's very easy to write a recursion of what happens in the next step.
Is that a result which is only valid for two-type processes?
So the set of equations you can write for K types, and you can write, I mean, it's just a messier matrix, right? Because now you have K squared number of different type of pendants, and you have K times K plus 1 over 2 different cherries. So you just are holding bigger matrices, but the results hold. And you can do it in the fact that you can have the rates be time dependent. The results below that you can infer back is not for time dependent. So virtually at this point, right, you're keeping the rates always constant in time, which is not what you would have if you took the phylogeny of a birth-death process, because your probability of making it to some time later is time dependent, right? But for now, the result is, well, my PhD student hasn't graduated yet, so there's some hope. Yeah, this result is for a time-independent branching rates in the multi-type.
So you don't need to know other functions or other configurations with
No.
like tree?
Yeah. Cherries and pendants. You have enough, essentially, if you look at the number of parameters and the number of quantities, they match. Okay, and this is where I finish my talk, and thank you for your attention.
Very much there, and for being the first speaker this morning to actually look at the sheets. It shows some sign of recognition of numbers. Very impressive.
Yeah.
So you have so you say that mathematically you have this inversibility property that is sufficient to know these fractions.
Yeah.
To know exactly the parameters.
Yeah.
But is there a way when t is fixed and you don't know the fractions? Is there a statistical result on like the difference of these parameters? When t is fixed and you only have like, suppose you have one tree and
Yeah, I don't know. Yeah.
so it's just the analytical result.
Yeah, I mean, I don't know because we haven't thought about it that long.
But essentially what you have is sort of expectations rather
Yeah.
than the likelihood, right?
Yeah,
You don't
exactly.
have the,
Yeah.
yeah.
We started first from just you're doing means. So, yeah. If anyone knows of results in multi-type trees, I'd be happy to hear about it, because Google Scholar is not helping me that much. Yes.
When you look into the subdominant eigenvalues, do you see the similar properties than in a regular Markov chain, that you basically know how deep you actually need to go in time to figure out your rates?
Haven't thought about it. Good question. I haven't thought about that at all. I mean, here we're just doing things based on the maximal growth, the principal eigenvalue. But yeah, she's working as we speak. So. Maybe one. I don't know. No, we haven't thought of it. But it's an interesting question.
If not, let's thank all this morning's speakers and reconvene at 2 o'clock.